Hi, I thought it'd be interesting to take a look at fitness functions that we're using currently for the chess contest and some fitness functions that might be better than the ones we're using right now. This is basically what we're using right now. This function here where we have the observed value of the game. It's either a loss for white, a draw, or a win for white. And then we have our prediction right here. Since it's observed minus predicted squared, this is what the function looks like. If we make a perfect prediction, there's really no error. You can see right along this line here. If we observe a win and we have predicted a win, then there's no error. Same with a draw and same with a loss. If we observe a loss and predict a loss, that's what it looks like. And the worst we can do is have 1 unit of error. If we predict, for example, a loss and yet we observed a win, that's the worst case. And so this gives an idea of the curve, the function curve, in the case of a win for white, and then this is what our prediction is. If we predict a win, then there's no error. If we predict a draw, then we have about this much error, and if we predict a loss, then we can have the maximum error here of 1. Now all that really matters, of course, is the slices of an observed win, an observed draw, or an observed loss here. Now, the current system that we're using is an aggregated system where we don't just consider the results of one game, but we consider the results of one person during an entire month. And so if we look at this over here, we'll see that the predicted values can be more than just 1, and they can go as high as however many games the person played during that month. So the difference here is the error can go huge because it is a squared error. And so, for example, if we were to predict that a particular person would have lost all of their games, but they actually won 10 games, the error is 100, much considerably higher than if we were to just have mispredicted each game individually. The error would have only been 10, a total of 10. But in this case, it could be 100. So the aggregated system seems to make it easier to exaggerate the errors, over exaggerate the weakness of a particular model. Now, what has been suggested by Mark Glickman is a function more like this. This is an interesting function. It's basically a log likelihood function, and you can see here it has a completely different shape to it. One interesting thing here is even if you predict, let's say, a draw, and you observe a draw, this function will get a little bit of an error to it, even if you make the perfect prediction. But it definitely rewards you if you go out on a limb. So instead of just taking the middle of the road, but you go out on a limb and you predict, for example, a win, and there was in fact observed a win, then you lose no there is no points lost. Basically, there's no penalty. But the opposite is interesting, because if you predict a let's say a win, but in fact observed was a loss, well, you can see this curve as it goes up here. Let me turn it around here. It goes up to infinity and beyond, as they say. So if you go way out on a limb and you're wrong, the penalty is infinity. So with this system, you would never want to go out on a limb unless you really were 100% sure. You are rewarded though when you go out on a limb and you guess correctly. And if you just always go middle of the road, in a sense you're penalized for just kind of trying to fudge it. So now again, what really matters though is the curves that are observed at 0, at 0.5 and 1. There's really only those 3 slices through this function that matter. Let's take a look at the slices. This is what the log likelihood function looks like in the case where a win actually occurred. Now if we predict a win right here, well, then we're in good shape. We will have a condition where there's no penalty. But you can see, as if you predicted a draw, there's a penalty in the case where a win occurred. And then as you more and more think that you're going to lose, it approaches infinity. As you finally, if you said 100% chance there's a loss, well, the likelihood of that, the log likelihood, is infinity. So let's take a look at the draw curve. It's a little bit different. Here, even if you predict a draw and a draw occurs, that's the best you can do. But you are penalized a little bit here. If a draw actually happened and you start going out on the limbs predicting a loss or a win, then you can see it also approaches infinity as you go way out on those limbs when a draw was the actual observed result. And finally, in the case of a loss, it's symmetrical, so that you can see here, if a loss actually occurred and you predict a loss, great, you're in good shape, and so on. And as you more and more thought there was going to be a win, the log likelihood just goes toward infinity. So we can take a look at all 3 of these curves at the same time. This is what it looks like. And you can see that they all meet at this one point here. The green is the curve for when a win was observed. The red is when a loss was observed, and then this sort of a gray area here is when a draw was observed. This point right here happens to be 0.693147 right here, and that is, if you were to predict a draw for every single game, that's the penalty you're going to get on every result. So what this system does is it tries to encourage you to go out on a limb. For example, make the prediction that white is going to win, and you'll have no penalty for that. But as you risk it, if you're wrong and the actual observation is a loss, for example, and you're risking it out here, well, now the penalty just starts going crazy. So you risk it, but you don't want to go all the way out on a limb, otherwise you'll really be in trouble.